You'll remember we left off talking about converting from scientific notation to decimal notation and vice versa. So 4,600,000, that can be written as 4.6 times 10 to the 6th rather, because you move the decimal point 1, 2, 3, 4, 5, 6 places. And it was a very large number you started with. Now we can talk about computations with scientific notation. It's going to look worse than it is. Let's look at something. If you have, say, 3.25 times 10 to the 5th power, if that's your number written in scientific notation. Well, 10 to the 5th is an actual number. This is an actual number. It's not just some symbols. That's 10 raised to the 5th power. In fact, this is 3.25 times 10 to the 5th would be a 1 with 5 zeros after it. So it'd be 100,000. That's actually why we move the decimal point as many times as we do. 5 places to the right. If I multiplied by 10, there's 1 0 after the 1. You move it 1 place. But here I've got 1, 2, 3, 4, 5 places to the right. So this moves 5 places to the right as well. Now for small numbers. Let's say you had 6.2 times 10 to the negative 4th. 10 to the negative 4th, this part, is actually equal to 1 over 10 to the positive 4th using the negative exponent rules we studied last week, which becomes 1 over 10,000. So you're actually doing 6.2 divided by 10,000 in that case. And so we move the decimal point to the left 4 units. And so what we're doing, scientific notation, the whole point is that the 10 and the power on the 10, they're not just arbitrary symbols, they are actual numbers going on. So if we want to do computations, if we wanted to do (2.5 times 10 to the 3rd times 3.1 times 10 to the 6th. In other words, if we were multiplying, what you can do is you can rearrange. You can rewrite that as 2.5 times 3.1. You can put those numbers together. Then you can do times 10 to the 3rd times 10 to the 6th. You can put the base 10 numbers together. So 2.5 times 3.1, we can do that over here on the side. 10 to the third times 10 to the sixth, we can use our multiply or our product rule, I should say, for exponents. That's going to become 10 to the 3 plus sixth power, so 10 to the ninth power. Over here, we'll do 2.5 times 3.1. It's kind of like 31 times 25, but then we'll just have to put a decimal point at the right place in the end. We start with this 1. 1 times 5, 1 times 2. We go to the next row with a 0. 3 times 5 is 15, so 5, carry the 1. 3 times 2 is 6, plus 1 is 7. Do our addition. And then remember, we had a total of 1, 2 decimal points here between the numbers. So our final number is going to have 2 decimal points after 2 places after the decimal point. So this is going to end up being 7.75 times 10 to the ninth. So 7.75 times 10 to the ninth ends up being our computation there. So whenever you realize that 10 to the third and 10 to the sixth are just numbers, they can be combined, and then we can do things like this, which is pretty useful. So here's a good one to work. It says write the number in scientific notation. Well, wait a minute, that's not in scientific notation technically. It looks like it, but this first number here has to be between 1 and 10. So this number, which we would call A, lowercase A has to be greater than or equal to 1, but less than 10. 0.8 is less than 1, so it doesn't count. It's not in that. Okay, that's all right. It's not technically in scientific notation. But that's still 0.8 times 10 to the third is actually 1,000, a 1 with 3 zeros after it. Which means you're going to move the decimal point 3 places to the right. 1, 2, 3. Thus, it's 800. $800 then, here's where the decimal point is. 800, you have to move the decimal point twice to get 8.0 times 10 raised to the, and you move the decimal point twice, so it's 8.0 times 10 to the second power. And now that's in scientific notation, because this first number here is between 1 and 10. So that's the answer here. So be careful, make sure the number is actually written in scientific notation. If it's asking a question like this, that means the starting number is not actually in scientific. Let's try out this one. 3 times 10 to the 7th multiplied by And we know it's multiplied because they're just two parentheses butted up against each other. This can be rewritten 3 times 3 times 10 to the 7th times 10 to the minus 4 power. So we'll do it piece by piece. What is 3 times 3? 9. Then these two 10 powers, they can be brought together. It's going to be 10 raised to the 7 plus negative 4 power. We're going to add those powers. Thus, that's going to be 9 times 10. What's 7 plus negative 4? 3. Exactly. 9 times 10 to the third. Then we notice it wants the final answer in decimal notation. So 9 times 10 to the third, take the number 9, you can call it 9.0, and move the decimal place 1, 2, 3 places. You'll get 9,000. So 9,000 is our final answer on that one. Let's keep trying this out. A couple more computations. Now we're talking about division. That's okay. 6 times 10 to the 4th divided by 3 times 10 to the 6th. You can rewrite this as 6 over 3 times 10 to the 4th over 10 to the 6th. And we'll do them separate. What is 6 divided by 3? 2. 10 to the 4th divided by 10 to the 6th, they have the same base of 10. So we can call that 10 to the 4 minus 6 power. What's 4 minus 6? Negative 2. So it's 10 to the negative 2. So it's 2 times 10 to the negative 2nd power. So we can even, we'll put the little x multiplication symbol because x is going to give it to you. Yep, I'm from the early 2000s, friends. So we have 2 times 10 to the negative 2nd. It wants us to write it in decimal notation. It doesn't want us to write it in scientific. So we just need to make the conversion. We're going to move the decimal point on 2, left 2 spaces. 1, 2. So that's going to be 0.02. We fill a 0 in here. Decimal point goes here. So fun stuff. Are y'all liking the fact that I'm working actual homework problems with you? Good, because I mean, that's what you're going to see. The numbers are going to be different for you, but I think it's at least along the lines of what you're seeing. I can't promise we can always do that. We certainly can in this case. Okay, now this one is a multi-part problem. See, it says 2 parts remaining. It wants you to do this computation. This, I think it's 72 million times 6 billion computation. It sounds like massive numbers, but we're going to first express the numbers in scientific notation. Then we're going to realize it greatly reduces the strain of making it work. The first thing we're going to do, we're going to simplify each number and write it in scientific notation. So 72 million we would have had to move, here's the decimal point, 1, 2, 3, 4, 5, 6, 7 spaces. So it's 7.2 times 10 to the, is it a positive 7 power or negative? Positive, because 72 million was a massive number. So it's 7.2 times, let's see if it'll accept it the way I want to write it. Yep, 7.2 times 10 to the 7th. So we got that number. Now we need to put 6 billion in scientific notation. Here was the decimal point. You're going to have to move it 9 spaces. So that's going to be 6.0, or just 6, times 10 to the positive 9 power. And it accepts that. 6 times 10 to the 9. Now it wants us to do scientific notation to do the multiplication, meaning it wants us to do 7.2 times 10 to the 7th times 6 times 10 to the 9th. We're going to rearrange things. We're going to do 7.2 times 6. Then we're going to lump together the 10 to the 7th and the 10 to the 9th. It's all multiplication anyways. So commutative property says I can move everything around. We'll start by doing 7.2 times 6. We're running out of space. Let's see, 6 times 2 is 12, carry the 1. 6 times 7 is 42, plus 1 is 43. 432, there was one total decimal point between all the numbers. So this carries one total decimal. So it'll be 43.2. I'll have to rewrite some of this. It'll be 43.2 times 10 to the, we'd add their power. 7 plus 9 is what? 16. Now we're not quite done here because this is not scientific notation anymore. The first number here has to be between 1 and 10. You can't help that because 7.2 times 6 ended up being greater than 10. So we're going to fix that. We're starting with 43.2. We're starting with a larger number that's going to add 1 to the power on the 10 to compensate. So we're going to end up with 4.32 times 10 to the 17th. Let's see. So lastly, we'll try this one out. We're going to write each of them in scientific notation first. That's 5,700,000,000,000,000,000. We'd have to move the decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So it would be 5.7 times 10 to the 12. Divided by we'd have to move the decimal point 1, 2, 3 times. So it'll be 1.9 times 10 to the, will it be a negative power? Yes, because we started with a really small number, a number greatly less than 1. Now we want to do the division. We're going to break this up into 5.7 over 1.9. We're going to have 10 to the 12 over 10 to the negative third. Now 5.7 divided by 1.9 sounds bad, but it turns out it's going to go cleanly just 3 times. You can move your decimal point. So that's the same as doing 19 into 57. And it turns out that's just going to be 3. If you're trying it out to figure out how many times does 19 go into 57, it turns out it goes in 3 times and it's clean. There's no remainder there. So this is going to be equal to 3 times. Now we're doing 10 to the 12th. And remember, we subtract the bottom power, which just so happens to be negative. So that actually becomes 3 times 10 to the 15th. 12 minus negative 3 becomes 12 plus 3. So we end up with 3 times 10 to the 15th, which is going to be a hilariously massive number. It's going to be a 3 followed by 15 zeros, which is 3 quadrillion. So a quadrillion is 1,000 trillions. If you had $1 trillion, which would be more money than you could probably ever spend on your own, imagine having that 1,000 times over. That's what a quadrillion is. Just like a billion is 1,000 millions. You have a million 1,000 times over. Okay. The last concept we're going to look at together is a concept called multiplying binomials. What is a binomial? Well, the prefix bi means 2. Bi means 2. Tri means 3, T-R-I. There's a couple prefixes for 4. You can do quad. The other one is not popping into my brain at the moment, but quad is another one. But you would say bi is 2. Think of billion. You start with, you have billion, then you have trillion is the next one, so you're counting up. A binomial is nothing more than a 2-termed expression that can't be simplified any further. So some examples. A few of them. 3x plus 7. That's 2 separate terms. Terms are separated by addition or subtraction. So that's 3x plus 7. Can you combine those terms together? No, they're not like terms. Like terms have to have the exact same variable construction, which these don't. This has the x variable attached to it. This has no variable attached to it. So they're not like terms. You can get exotic with your variables. You could say 3s minus 4t. You can use s and t instead. Are those like terms? No. So they can't be reduced any further. They're separated by subtraction. And that's all she wrote. There's nothing we can do about it. It's as simple as it gets. You know, like I said, you can get 2x squared plus 3x. Those are not like terms because one has x squared, the other does not have the squared component, so they are not the same variable setups. So these are examples of binomials. A non-example, something that's not an example, would be 3x plus 6x. It looks like a binomial because it's separated by addition. The problem is those could be combined into 9x, which is not a binomial anymore. So a binomial specifically, you can't have any more combined terms to reduce the amount of terms you have on there. This is truly a one-term expression masquerading as a two-term expression. Falsely, it's a wolf in sheep's clothing. So a binomial is a two-termed expression. What we can do is we can talk about multiplying binomials using a cute little method called FOIL. I've always said it's your favorite four-letter F word in mathematics, FOIL, because of how much it shows up. Imagine you are multiplying these two binomials. Each of them individually is a binomial. This whole thing is no longer a binomial, but this by itself is a binomial, this by itself is a binomial. And we're multiplying them together. How many of you remember FOIL straight up? You've seen FOIL before? FOIL is going to be a little acronym. It's going to stand for the following. First, which means we multiply the first two things in there. The first expression of this term times the first expression of this term. The next one is going to be the outer terms. 3x and minus 1 are on the outsides. They're the outer terms. Next, you're going to do the inner terms. These two get multiplied together. And then you're going to do the last terms. And then I'll bring it all together into a new expression that you're going to form. All told, you're multiplying every term in the first expression with every term in the second expression. In fact, that's the general distributive property. Doesn't matter if you have two binomials or not. FOIL is just a cute little memory trick if you happen to be multiplying two binomials only, which is what we're doing. So let's actually apply it. I'm going to erase this. Well, I guess I can leave that up. I'll erase this business so it's easier to look at. So the first thing I'm going to multiply is the 3x and the 2x. Those are the first terms. Then I'm going to do the 3x times the negative 1. And since it was positive 3x and negative 1, you can just say minus 3x times 1. Then it's going to be plus, it's positive 7 times positive 2x. So it's plus 7 times 2x. Then it's positive 7 times negative 1, so it's minus 7 times 1. Now here's how this is going to work, this first term. You can do the 3 times 2, then you'll do x times x. Then what's 3x times 1? Does the 1 change it? So it's just 3x. Plus, what is 7 times 2? 14. And then there was that other x attached there. That doesn't go away. And then finally, minus, what's 7 times 1? 7. So the only thing giving us any bother, 3 times 2 we know is 6. How do I combine these x's together? Exactly, that's x to the first times x to the first. So to bring them all into a single x, I add the powers, 1 plus 1, so it's 6x squared minus 3x plus 14x minus 7. Now, an old rule of thumb in mathematics, and this is one we've talked about already, if you can combine like terms, should you? Absolutely. Are there any like terms here to combine? Exactly, 6x squared. I have minus 3x plus 14x. What does that combine into? Plus 11x, exactly. And then there's that minus 7. And so that is going to be how we multiply out binomials like that. You multiply two binomials, you can use the FOIL method. What'll really cook your noodle, and it's something we don't study in this course, is if you wanted to start with this thing at the bottom here and re-express it this way. That's called factoring. Going the opposite direction is called factoring. Again, we're not going to be worried about it here, but just an interesting term. So let's return to the homework and work some of the ones they have for you. Why I do not want to select the one I told you to select. Okay, so here this is like a deconstructed problem where they're having you work it piece by piece. It's saying for x plus 7 times 11x plus 2, we do the product of the first terms. You do x times 11x. Which of these will it be? Well, that's a 1x times an 11x. The 1 gets multiplied to the 11, so the coefficient's going to be 11 as well. Then you have an x times an x, which is going to give you x squared. So maybe we don't have to necessarily do this one together. Let's just jump right in and work some of these. That's an easier one. We want one a little more challenging than one we just worked. This should be fine. Or no, we'll go back. Sometimes simple is better. We'll try this one. X minus 1 times x plus 3. First, you're doing x times x. You're doing the first terms, x times x. Then you're doing x times 3, and it's addition because it's positive x, positive 3. I'll write it like this at first, but we're going to notice that's kind of awkward, so we'll change it in just a moment. So we do the first terms, x times x. The outer terms, x times 3. The inner terms, negative 1 times x, that's just going to be minus a 1 times x. Then finally, a negative 1 times 3 is going to be minus 1 times 3. Now just simplify, combine like terms, and call it a day. What's x, which is really x to the first, times x to the first going to give you? X squared, exactly. You're going to add the ones together to bring it into a single x. And then there was no coefficients to multiply. The coefficient is secretly 1, but we don't have to write that. Now I could say plus x times 3, but that's kind of awkward. I'm going to call that 3x and not lose any sleep over it. Then I have minus 1x, but that's just minus x. And then finally, minus 1 times 3. Are there any like terms to combine? Usually with FOIL problems, yes, there will be some. Not always. I can give you one where there isn't. But 3x minus x, what will that combine into?
4.
Not 4x. 3x minus x. So 3 minus, yeah, exactly. 3 minus 1, basically. So we're going to have x squared. So foiling, we're multiplying out, we're expanding. Factoring, we're doing the opposite. We're starting with something that's expanded and trying to condense it into products. Let's see about working one more. Come see about me. They want you to watch some video, but we won't watch the video. We will just multiply this out ourselves. Someone give me a color that you'd like to see. Blue, orange, brown, green. Orange, I love orange. So we're doing 3x minus 4 times 2x plus 5. We're going to apply our FOIL technique. 3x times 2x. Let's see if we can do that one quickly. You do the 3 times the 2, which is? You do x times x, which is what? X squared, exactly. Now we're going to do 3x times 5. They're both positive, so we're adding. 3 times 5 is what? And then the x doesn't have anything to combine with. It just stays there as x. Now we're doing negative 4 times positive 2x, so it's going to end up being negative. What's 4 times 2? 8, and then there's just an x there. You can't escape it. And then finally, negative 4 times positive 5 will be what? So it'll be minus 20, exactly. Then we just combine like terms. What's 15x minus 8x going to give you? 7x, and it's positive. And that's all she wrote. And that's multiplying binomials. That's actually the last bit of the 0332 portion of the class. So don't go anywhere.